on your phone. When we're talking about plugging in or connecting electrical devices, you'll need to know the parts of a 3-pin plug. It's got 3 wires. The live wire, you can see that live brown wire on the right-hand side of the picture there. It's the one which carries the current in through the plug socket. And its potential difference is constantly changing, plus minus, plus minus, plus volts, minus volts, plus volts, minus volts. The opposite side of the plug has the neutral blue wire. It's the one which completes the circuit, and it's sitting there at 0 volts compared to the live wire. So the current is constantly flowing in and out, with the neutral wire completing the circuit. The earth wire, the yellow and green one, it's a safety wire, which makes it much less likely you'll get an electric shock. About that in another slide. In terms of describing what the plug is built from, the outsides of plugs should be made from an insulator, something like rubber or plastic, so they won't conduct electric current through them. You're not going to get a shock. But the actual pins, the metal bits, are made from brass. It's a hard metal which won't bend and is a good conductor of electricity. The fuse, you can see there, connected to the live wire, is another safety feature which we'll talk about. It'll break or blow or melt if too much current flows through there. And the plug itself, the cables are all connected in there, held in there I should say, by a plastic cable grip which is screwed down, so it's unlikely to pull the wires out if you kick the cable. How do the earth wires keep things safe? Well, you only need an earth wire on devices which have a metal case on the outside. The earth wire is actually connected to the metal outside bit of this object. There we go. Got a metal cooker here. Got an earth wire screwed into the bottom of it there. That earth wire means that if for any reason something goes wrong, for example, our live wire here comes loose and touches the metal outside part of the cooker, and we could get an electric shock from it, what happens instead is the electric current flows down the earth wire and down into the earth, into the ground. As it goes out, it flows through the fuse and melts the fuse on the way down. So it prevents us getting an electric shock, but it's only needed on objects that have a metal on the outside. The fuse is another safety feature. It's got a little bit of wire in the middle of it there. That wire is set up so it can melt quite easily as it gets hotter. Why is that useful? Because if too much current flows through that fuse, then the wire will get so hot that it melts, and that will break the circuit. So that stops too much electric flowing through that circuit. Another way of protecting too much current from going through a circuit is using what's called a circuit breaker, or an RCCB. They use magnets to very quickly break a circuit. They work by detecting any difference in the current going in through the live wire and out through the neutral wire. If there's any difference in that current, it knows there's a fault in the circuit, and it breaks the circuit very quickly. They are much, much faster than fuses because they don't have to heat up and melt. And the advantage is you can reset them simply by flicking the switch on them once they've broken the first time. Final safety feature you need to know is what's called double insulating an object. If something is double insulated, it'll have this symbol on it, a box inside a box. It tells you that the inside casing or the casing of the object has been lined with plastic or another insulator. That means that if for any reason the live wire does come loose or there's a problem inside there and is touching the casing, it cannot send electric current through there, so you can't get an electric shock from it. Even though it might have a metal casing, the inside is lined with plastic. If you want to calculate how much current should be going through a plug to pick the right fuse to go into that plug, the best equation to use is this one, PIV. Pigs in Vales, power, current, potential difference. If you know the power of the electrical device you've plugged in and the potential difference, which should be 230 volts here in the UK, you can work out how much current is going through it and put in there. There is another equation which you can use to work out current. P equals I squared R. Power is the current squared multiplied by the resistance. Pigs in square rooms, so an alternative for working out the current through an object there. We need to talk in some detail about what the electric current actually is. What's going around the circuit? Well, it is lots and lots and lots of tiny little charged negative electrons that are being pushed around the circuit. The potential difference from the battery gives them energy and pushes them around. So our definitions for 1 mark is that current is a flow of charge or a flow of negatively charged electrons around the circuit, and the potential difference is how much energy those electrons, that charge, carries around the circuit through each part of the circuit. So the PD we can define as the work done, or the energy transferred, by each unit of charge that goes around the circuit. That gives an equations. The first one, if we want to know how much charge has flowed around the circuit, we multiply the current in amps by the time in seconds. That gives us our Queen intent equation. And also, if we want to know how much energy has been transferred as the current flows around the circuit, we multiply the potential difference by the charge. So that gives us earthquake volcanoes for our final equation. That E for energy, Q for charge, potential difference there. There are different types of electric current that can flow around a circuit. One sort of current that flows around is what's called alternating current, where the potential difference is changing between plus and minus, plus and minus, plus and minus, telling us that the electric current is constantly changing direction. So constantly changing direction means an alternating current. That's what our mains electricity is. If it's produced by a generator spinning around, then the electric current is constantly changing direction. The current coming out of a battery or a solar panel is only being pushed in one direction, so it only has a plus or positive potential difference. Its potential difference stays the same the whole time. It's only flowing in one direction. So constantly changing direction gives you an alternating current. Only flowing in one direction gives you a direct current. Here in the UK, our mains electricity, you need to learn these numbers, has a voltage of 230 volts and a frequency of 50 hertz. That means it changes directions backwards and forwards 50 times a second. 230 volts and 50 hertz. The system of transferring the power around the country from the power stations is called the national grid. The electricity generated in the power station is first of all sent through what we call a step-up transformer. That increases the voltage, even though it's come out of the power station at about 25,000 volts. It gets stepped up, increased by that step-up transformer to hundreds of thousands of volts, 440,000 volts in this example. But before it gets into our homes, we use something called a step-down transformer to reduce the potential difference again to 230 volts. Why do we send it at such high potential difference through the power cables? Well, because if we increase the potential difference, that decreases the current. And why do we want low current? Because it's current that heats up wires. So as the wires are getting hotter, we are wasting energy, losing energy by heating. So the lower current means we lose less energy as the power is transferred from the power station to our house. It's really just a consequence of the PIV equation. If you want to keep the power the same, if you increase the potential difference, then you're decreasing the current.